Start. Okay. So I do think I need to say a couple of things about the exam because there have been a few fairly common questions about the grading. So in particular, there's a fairly common mistake or omission that lots of people left out in question 2, which is the question about pulling all-nighters. That there were several answers of that. Sorry, stupid thing is not working. There were several answers of the form. Let's consider the maximum possible score that we can get up to or starting with the ith assignment, assuming that we have just pulled k all-nighters, unquote. And that is a reasonable start to a solution, but there's an unfortunate ambiguity in that phrasing, which is, first of all, several people said, suppose it is day I, without explaining whether they were computing the maximum score they could get on assignments 1 through I or in assignments I through N. And it matters because depending on whether you one or the other, you're going to get different recursion patterns. But then more subtly, when they said, let's suppose I'm thinking about assignments I through N, and I start having just pulled k all-nighters, does that include the night immediately before assignment I or not? And again, depending on the choice you make about exactly what k represents, you get slightly different recurrences, which will still lead you to a correct algorithm either way. But this also meant that because there was some ambiguity in the statement of the English description of the problem, there was also a relatively common off by one error in the recursive cases. So you would intend to mean, no, I'm not including the night immediately before assignment I. But then you would say, oh, and if I pull an all-nighter for assignment I, that's the kth all-nighter, and so you'd divide out by 2 to the k minus 1, which is inconsistent. And so that ambiguity actually cost some people points, both in your English description is a little vague, and you have a minor error in your recursive case. English descriptions of the form, max of ik is the solution to the problem when I have I problems and k all-nighters, are not sufficient because I really want an English description that is detailed enough that I can rip off the top of the page that has the statement of the problem and still have a well-defined statement that includes I and k as nouns in the description that explain exactly how they're going to be used. And so this was, for a lot of people, this resulted in a minus, 1 or 2 points off in the solution for problem 2. The other case that is relatively common and several people have asked me questions about was in the induction proof in problem 1. There's a statement about needed explicit case analysis, and the usual response is, but I have an explicit case analysis. It says base case here and it says inductive case there. And that's not actually what an explicit case analysis means. So you're supposed to prove a theorem about arbitrary positive integers. I should be able to see, oh, here you're considering the case n equals 1, here you're considering the case n equals 2, here you're considering every integer bigger than 2. And if you don't actually explicitly say, I'm considering integers bigger than 2, then when you try to apply the inductive hypothesis at n minus 2, it might not work. So the reason to state the boundaries of the cases explicitly is, again, to make sure that you understand exactly when your inductive argument works and when it doesn't. And the reason to do that is that's how you come up with the base cases in the first place. The way that you should be thinking, the way that I advocate thinking about induction is exactly the way that you would think about writing a recursive algorithm. First, write down the argument for the most general case you can think of. And if you like, if it comforts you to write inductive step right before it, fine. But figure out the most general thing you can. It may or may not actually invoke the induction hypothesis. May not invoke the induction hypothesis at more than just the previous value of n. Doesn't matter. You figure out the most general argument you can, and then you figure out under exactly what circumstances that argument fails. And those are other cases that you have to handle explicitly. And so you do that again. You say, out of the cases that I haven't handled yet, what is the most general statement I can make? And the only difference between a base case and an inductive case is a base case doesn't invoke the inductive hypothesis and an inductive case does. But that's not something you know in advance when you start thinking about the cases. That's something that falls out at the end. Right? My reason for wanting you to give me an explicit case analysis in the preferably in the style that is in the actual midterm assignment, midterm solutions, is I want to know that you understand the boundaries of where the inductive case actually works, and you're not just parroting the structure. You actually have some understanding of what's going on. In any case, this is, at most 1 or 2 points. This is not going to make the difference in everybody's grade, but this penalty was applied consistently across everybody. So I'm happy to look at your exams if you fall into one of these categories that I'm talking about and verify, yeah, this was the problem, and talk to you about it. But because the standard was applied by the same grader to the same problem for everybody, I'm going to be a little bit hesitant to give points back for that, because I'd have to give points back for that for everybody, and the net effect of that would be just to raise the curve by a point, which means nothing. Okay. Are there any other questions about the midterm, the way the midterm was graded, which you're willing to ask in public? I recognize that many of you may have questions about your particular midterm that you don't want to necessarily shout out to the entire class. Okay. So hopefully my pencil works. Good. Okay. Before I say anything else, I do need to apologize for not making my expectations universally clear to both the homework graders, the TAs, and to the class, so that everybody went into the exam and went into the grading exercise with a common understanding of what was actually being asked and what we were actually expecting. That's on me. I didn't communicate that effectively to everybody. I'll do my best not to repeat that mistake for the second midterm and the final exam. Okay, so what we've been talking about for the last couple of classes is a pair of optimization problems called maximum flow and minimum cut. I'm not going to go through the detailed definitions again. You've already seen me do that a couple of times. But I want to, at least remind you of the kinds of things that we did yesterday. So the general algorithm that, or the class of algorithms that we use to compute these things is a so-called augmenting path algorithm, where I construct a residual graph. I see if that residual graph has a path from S to T. If it does, I push as much flow along it as I can, and then I repeat. If it doesn't, then I know that the flow that I've accumulated so far is a maximum flow. And implicitly, this is representing the maximum flow as a sort of a weighted sum of paths. Right? And more generally, there's this path decomposition theorem that says if I give you any flow, you can't necessarily decompose it into paths by themselves, but you can always take any flow and decompose it into a weighted sum of paths and a weighted sum of cycles. And moreover, the number of these things is at most the number of edges in the graph. It's actually strictly smaller than the number of edges in the graph, but the proof that I sketched in class isn't going to give you that. The other feature of this is that if you have integer capacities, you're going to end up with an integer flow. Meaning, if the capacity of every edge is an integer, then after I run the Ford-Fulkerson algorithm, or any variant of the Ford-Fulkerson algorithm, the flow that I get out as the output of the algorithm will assign an integer flow value to every vertex, to every edge in the graph. And that integrality actually turns out to be important in some of the applications we'll talk about today. And then yesterday I said, on Tuesday, there's this question of, which path do I augment along? If I don't specify which path, then I assume that I'm leaving the choice of which path to augment to an incompetent or malicious adversary who's going to choose the paths badly for me. So if I just say arbitrary, then the guarantees are pretty bad. You can guarantee that if you have integer capacities, the algorithm will eventually halt, but it may take time exponential in the number of bits you need to write down the input. If you have irrational capacities, or you think of the capacities as just real numbers, you can't even guarantee that the algorithm will halt, or that it even converges to an approximation of the correct answer. And then there are these two, so in the case of integers, you get something like E times capital F, where capital F is the value of the flow. If you do the first thing that occurs to you to do, if I say, what would be a good path to push flow along? Namely, I should find the path that allows me to push the largest amount of flow that I can. This will actually take you a little bit longer to find that path. It's no longer just a whatever first search. You actually have to do something that resembles Dijkstra's algorithm. But then you can guarantee that after E log F iterations, again, assuming integer capacities, that the algorithm will terminate. And then a slightly less obvious thing to do that turns out to be better is I should pick the path from S to T that has the smallest number of edges. And here, there's an argument that I didn't actually give the details for that appears in the notes, that essentially you can argue that the distance in the residual graph from the source to any particular vertex can never decrease. It only goes up over time. And morally, at least, every time you augment something, at least one distance gets bigger. And if you push through the details of this argument stated correctly, that implies that the number, after EV iterations, you must have halted because otherwise some vertex is further away than it's possible to be from the source. And then actually finding this path is just running breadth first search, so it takes linear time. And then finally, there's Orland's algorithm, which runs in E times V time. This is really the best you could possibly hope for any variant of augmenting paths because of this flow decomposition. The flow decomposition might need this much space just to write down. So any algorithm that even implicitly computes flows one path at a time or one cycle at a time is necessarily going to take this long. So generally speaking, when we talk about using flows, we're going to be using one of these two. And you might ask, why would I ever use just the arbitrary Fold-Ferguson rather than using Orland's algorithm? And the answer is, if all of the capacities in the graph are equal to 1, then the largest flow you can have is, well, I saturate every edge coming out of the source, and there are most v minus 1 of those edges. So I have a cut of size v minus 1, and every flow has value less than the cost of every cut. So the maximum flow value in the case where I have unit capacities is just v minus 1. Okay. When all capacities are equal to 1, the flow is at most v minus 1. And so in that particular special case, where I have a flow, all the capacities are 1, or they're either 1, 2, or 3, you can make a similar argument. The flow value is only going to be proportional to the number of vertices. And so I could just plug in v here instead of f. And in that special case, I've already gotten what Orland would guarantee. And unlike Orland's algorithm, you can actually implement Fold-Ferguson. Okay. It takes a bit of work because you have to figure out how you're going to represent everything, but I'm confident that if I gave you a week, you could do it, given on top of your other homework assignments and whatnot. Okay? So today what I want to do is start answering the question that somebody asked me a week ago. That's nice. I've defined this abstract problem. Why do I care? Right? What is this good for? And at the beginning, I'm going to start talking about applications that are themselves also kind of abstract. But over time, the applications that I'm going to talk about are going to become sort of less and less and less abstract, and more like things that one might actually want to do. Okay? So at the start, I'm still going to be asking, here's a question you might ask about graphs, and how do we solve it? And the answer is going to be, oh, well, I massage the graph a little bit and I feed it to my maximum flow subroutine. And I get an answer back out, which I massage, and I get the answer I want to my original problem. But as time goes on, some of these applications are going to start out looking nothing like graphs. I'm just going to have some data that I need to figure out, and but somehow still magically flows are going to be the right abstraction to solve the problem quickly. Okay? So applications of flows and cuts. Okay. So I'm going to start off with something simple that is going to look almost exactly the same. This is called the edge disjoint path problem. Now I can tell a story here about Google Maps or FedEx or bus companies or something. So the fictional story is Google has a garage on the east side of Champaign-Urbana, and Google has where all the Google Maps cars are going to start. And Google has a garage on the west side of Champaign-Urbana where all the Google cars are going to end. And Google wants to send as many cars out into Champaign-Urbana as they possibly can, but this is in a bizarre universe where redundancy is bad, so Google wants to make sure that when they send a car down, say, University Avenue, that only one car gets sent down University Avenue. Okay, so for any block, I want to constrain the way the cars travel through town so that either one car traverses that block of street and takes pictures, or none does. Right? I don't want to be wasteful and have lots of cars going down the same street. So I can abstract that by saying, okay, I'm given a graph G, which has vertices and edges, and I'm given two vertices, which I'll call S for the start vertex and T for the terminal vertex. And what I want to find is the maximum number of paths from S to T that contain each edge at most once. Okay? So I can send the first path from S to T however I like, but then any edge that's traversed by the first path is off limits to the second path. Okay? So I believe you could tell me the answer to this. How do I solve this question? Yeah.
Model it as a graph with needed edge capacities.
Right. So what I'm going to do is for the solution is I'm going to give. Let me just say set the capacity of every edge to be 1, and then run just run for Fulkerson. Okay. Not quite. This is, on the homework, for example, I might ask you to actually spell out for Fulkerson or compute maximum flow. Otherwise, I think this is a line from a Marvel comic book. Run, Fantastic Four. And it's actually not exactly the end of the algorithm, because the output from Ford Fulkerson is a maximum flow. It's an assignment of flow values to every edge in the graph. And that's not what the problem asked for. The problem asks for it's a little bit ambiguous whether I actually want a maximum size set of paths or if I just want the maximum number of paths. But let's say that I actually want the maximum set of paths. I really do want the paths. I don't have them yet, so what do I do? Somebody, yeah.
While running the Fulkerson given, when you augment paths, you only take the path which has the least number of edges.
Okay. So I'll run the short pipe version without forward focus on.
And you will keep on counting the number, like keep on adding those paths.
Well, now remember, for any variant of forward focusing, including the one where I use the minimum number of edges, it's possible that in one iteration I'm going to push flow along some path. Here's T and here's S. And then in a later iteration, I might push flow along another path. And notice I've used that edge more than once.
If your capacity is 1, you will.
Yeah, but I used it once forward and once backward. And at this point, I sort of canceled that out. But even if, again, I was ambiguous whether the original graph is directed or not. So to keep this a little bit simpler, let me go ahead and just say this is a directed graph. Okay, so I first send 1 unit of flow along this purple path. Great. Now this reversed edge shows up in the residual graph, and the next residual path might take it. And then later still, I might send 1 more unit of flow forward along that same edge, and now my paths are not disjoint anymore. Okay. Also, one of them is using an edge the wrong way. Because the directed graph, I've built my city entirely out of one-way streets.
Whenever you add the roots to the path to a set, whenever you have this reverse edge, you somehow modify that previous set.
So I'm gonna advocate the standard meta strategy. There are 2 ways that I can attack this problem. One is think about the algorithms that we've already discussed in class and see if I can tweak the algorithm to solve the problem. The other is let's assume that the algorithms that we've discussed in class are black boxes which we can't touch. And let's see if we can tweak the input so that those black boxes actually give us what we want. Yeah.
Just to show in the dog, after you get the paths on the full focus, you just remove those edges and then run the thing again. And then that way you get path, and then the next path you're going to get is this.
So the suggestion, let me make sure I understand the suggestion correctly. You run forward focusing all the way to completion, or just one iteration?
All the way.
Okay, you run it all the way to completion, and then so I've got a bunch of paths. And now what do I remove from the graph? Let me take a suggestion back here.
It's unrelated to
Okay,
yeah.
we'll think about his. Well,
If I run the algorithm and I get the max flow, that means say the max flow is 5, means I can send 5 cars out, and 5 cars will end up in the
That's correct.
Right?
Yes.
So because the capacity is 1, that means no cars can go on the same edge. More than 1 car can go on the same edge.
Right.
And so can I just do find any path? I know the max flow, so I just find the path, delete it, and then do it again until I have.
Yeah. So this actually is not that different from what he was suggesting,
Oh. Okay.
and it's exactly the right thing to do. And we've seen that algorithm. We saw it go by really fast before, which is that was how we did this. Okay, the way that we proved the flow decomposition theorem is we said take any flow. If it's got cycles in it, wander around until you find a cycle and then take that cycle out. If it doesn't have any cycles in it, start at S and wander around. You'll eventually get to T because you can't get stuck anywhere else. That's a path, take it out. Okay. So the last step in this algorithm is actually compute the flow decomposition. Okay, so what would happen if, for example, this were the output, this was the way that Ford Fulkerson ran. And the actual flow in this case would only contain, you know, 1 unit of flow going along this purple edge, you know, something like this. Now notice, if every edge that I've drawn here, I'm imagining carrying 1 unit of flow. Any edge that I haven't drawn, I'm imagining carrying 0 units of flow. Now in this particular case, I don't have any cycles in the graph. So I can just start removing paths greedily. So I can find, for example, here's a path. Just remove it. Then, I don't know, here's another path. Just remove it. And then here's another path. Just remove it. And then I've got 3 paths that don't share any edges. Yeah?
So if we do it greedily approach, how do we know that's the max?
Because the way the proof of the flow decomposition theorem works is every time you find a path, let's say the flow is acyclic. Every time you find a flow in the path and you remove that path from the flow, you decrease the value of the flow by, in this case, 1. And then by the induction hypothesis, I'm left with a flow with value f minus 1, which I can decompose into f minus 1 paths. The algorithm as a whole, right, computing the flow decomposition takes VE time, running Ford Fulkerson takes VE time. And it's really VE, not VF, because all the edges had unit capacity. And so the overall running time of this algorithm is V times E. Now, if I'm being very careful here, I have to give a proof that, in fact, Ford Fulkerson will give me the right thing. And there are a couple of subtleties that I need to point out in order for this proof to go through. Okay, so one is Ford Fulkerson will give me a flow, but more importantly, because the capacity of every edge is an integer, Ford Fulkerson will give me an integer flow. But if the capacities of the edges are are all 1, the only possible flow values are either 0 or 1. And I had to actually notice that Ford Fulkerson will in fact give me an integer flow. This is not something that's true of all flow algorithms. There are other flow algorithms that are not based on augmenting paths that don't have this property. And then the second thing that I have to observe is that the flow decomposition theorem says if I have a flow with value f, I can decompose it into f paths. But conversely, if there are f paths from S to T, then the maximum flow value, then their sum is a flow with value f. And therefore, this is something that the max flow can actually compute. Okay? So the answer that I get can't be too small, because if I observed that if there were more paths of it was possible to go through this graph a different way and get 4 paths, that would have given me a flow of value 4. But I didn't. I got a maximum flow here. And the answer also can't be too large, essentially because the paths that I actually extract from here, when I sum them up, they do correspond to a flow. Okay? Good. So now let me make one change. Okay, I guess this is 2 changes. Instead of requiring that every edge, I'm sorry, was there a question? Okay. instead of requiring that every edge is used at most once, I want to require that every vertex, and I mean every vertex except S and T, is used at most once. Of course, every path from S to T is going to use S and it's going to use T. But I don't want any other vertices in common, which means this particular solution is not good because there are two paths going through this vertex here, and there are two paths going through this vertex here, and so this is not a sufficiently disjoint set of paths. I really want something where the paths don't touch at all except at their endpoints. Yeah?
You can simply split each vertex into
Right. So the basic problem is I've essentially got capacity constraints on the vertices, and we don't know how to deal with those yet. But we do know how to deal with capacity constraints on the edges. So let me turn the vertices into edges. And the way that I'm going to do that is for any vertex V, might have, you know, some edges coming in and other edges going out. I'm going to convert that into a pair of edges, or sorry, a pair of vertices, V in and V out. All of the edges that used to come into V, now I'm going to redirect into V in. All of the edges that used to go out of V, I'm going to redirect so they come out of V out. And then I'm going to add one more edge from V in to V out, and I'm going to give that edge capacity 1. Okay. Now, my claim, which I now need to prove, let's call the original graph that I'm given G, and let me call the graph after I've done this conversion H. What I claim is that the maximum number of vertex disjoint paths in G is equal to maximum number of edge disjoint paths in H. So once I've done this split of every vertex in the graph, except S and T, because I don't need to split those, then I can just refer back to my previous algorithm, which computes edge disjoint paths. Okay. This split can be done in linear time, and so this is dominated by the running time of the edge disjoint path algorithm. So I get order VE time for that. The only thing I need to prove is that this is in fact correct. Okay. So like most of these kinds of transformation, so-called reduction arguments, I really have two things to prove here. I have to prove that the number of vertex disjoint paths in G is at most the number of edge disjoint paths in H, and I have to prove that the number of vertex disjoint paths in G is at least the number of edge disjoint paths in H. Okay? And the way that I'm going to do that, so I have two things to prove. One, suppose there are k, vertex disjoint paths in G, then I want to prove that if you show me a set of k vertex disjoint paths in the original graph, I can find a corresponding set, the same number of paths in that are edge disjoint in H. Okay? So let me start by saying, okay, let's look at a particular vertex V, and let's suppose that these k paths include one path that goes through V. Now it has to be only one. There can only be one path that goes through V, because it says right here the paths are vertex disjoint. Now I want to construct, for those k-paths, the corresponding set of k-paths in H. And the way I do that is if I look at the path that goes through V, I'm just going to modify it so that it goes through the same edge into, instead of going into V, it goes into V in. And the same edge out of V, it's going to come out of V out, and it traverses this edge in the middle. Now, this edge is traversed exactly the same number of times as the corresponding edge in G, which is at most 1. I can't traverse that edge in G more than once, because then I would go into V more than once. Okay, so that edge is used only once in H. So likewise, this edge is used only once in H. And the number of times that I use this edge in the middle is also only 1, because there was only one path that went through V in the original graph. Okay. Then there are k edge disjoint paths in H. On the other hand, suppose there are k edge disjoint paths in H. Well, let me erase the previous details here. Okay. Now I have to think a little bit about how those paths would actually interact with this gadget. So it's sort of clear that if I could guarantee that each of these edge disjoint paths goes through one of these V in, V out edges, then I'm basically done. So I just contract those edges away, I go back over here. I can only have, because things are edge disjoint, in particular I have only at most one path that can go through the central edge. But I have to account for the possibility that there are paths in H that don't go through those edges. Okay, so let me think about one of the other edges in the graph. Say if something going into V in, if one of these k edge disjoint paths ever touches V in, then there's only one edge out of V in, and so it has to go through that. Similarly, if one of these edge disjoint paths uses this edge coming out of V out, there's only one edge going into V out. So that path must have come from this vertical edge. Okay, so every path in this set of k paths is going to have the form start at S and go to V in and then go to V out and then go to W in and then go to W out and eventually go to Z out and then go to T. Every path must look like this because all of the edges out of S go into some V in. The only edge out of V in goes to V out. All the edges out of V out go to something else in, and so on. Okay. But at this point, I can now take those paths and map them back onto G, just again by recontracting that middle edge. So I just transform this into S to V to W to Z to T. And because these paths use this edge at most once, the transform paths use this vertex at most once, and that applies to every vertex. So there are k vertex disjoint paths in G.
You need to copy this
case. There-
No, okay.
because-
So what I mean is, if there exists a set of k paths in G that are vertex disjoint, then there exists a set of k.
Exactly.
There exists a set of k. That does not rule out the possibility that there's more. All right. So really, what I'm proving is, in the first case, is this. And then the second one, if there are k edge disjoint paths in H, if I can demonstrate a set, then I can transform it into a set of at least k vertex disjoint paths in G. And so what this means is that for the first case, that the answer to the vertex disjoint path problem is less than or equal to the answer to the edge disjoint path problem. And in the second step, I'm proving that it's greater than or equal to. And together, those mean that the two quantities are equal. Okay. Really, what I'm doing is I'm setting up a one-to-one or one-to correspondence between sets of vertex disjoint paths in one graph and sets of edge disjoint paths in the other. So you're counting the same thing. Okay. Great. All right. So more generally, this kind of reduction allows me to put capacity constraints on the vertices. Right? So I can say, I have vertex capacities. So I could just require that for any vertex V, the sum of the flow values going into V is at most the capacity of V. Right? So I just set up, in addition to my edge capacity function, I have another function that assigns capacities to the vertices. And I'll add another condition to the definition of a feasible flow, which is that in addition to saying you can't push too much water through the pipe, you also say you can't push too much water through this joint where lots of pipes meet. Okay? And the same reduction where you take a vertex with capacity C and you transform it into a pair of vertices connected by an edge with capacity C allows you to reduce this vertex capacitated flow problem back to the original flow. Okay. This is a style of extension that we can apply to in lots of other ways. I'm not going to walk through the details of this, but for example, in the notes that describes a way of saying, suppose I want to guarantee that there's at least one unit of flow going through some edge. Then you can modify the graph in a way that will turn finding a flow that meets this additional constraint into just a standard maximum for the problem. Right? So instead of just having upper bounds on the flow, you could also have lower bounds on the flow. And because you can do it on edges, you can also do it on vertices. You can say, I want this edge to carry at most 1 unit, this edge to carry at most 3 units, this edge to carry at most 5 units, but I want at least 4 units to go through this node. And then again, by this nesting these transformations, you can reduce back to an original standard flow problem without blowing up the complexity of the problem at all. Good. So, questions about playing with vertices? All right, so let me change it. Yeah, I'm sorry.
How do you apply the lower bound?
I'm sorry?
So this is how do you apply the upper bound for the vertex? How do you apply the lower bound?
The same thing. If I have a lower bound on the vertex, I expand it into an edge, and now I have a lower bound on the edges. And then I apply the reduction that takes lower bounds on the edges and turns it into upper bounds on different edges, which I haven't told you. I can let you look in the notes for that, but yeah.
Is this all for acyclic graphs?
No. Even if the graphs have cycles. So the important thing is that you redirect all the incoming edges into the inside of the vertex, and you redirect all the outgoing edges from the outside of the vertex. So essentially, in other contexts, I would refer to this as a vertex gadget. Right? I have a bit of the output of my transformation that a piece of the output graph from my transformation that corresponds to a vertex in the graph that I'm given originally. And these pieces that I build the final graph out of are often referred to as gadgets. Okay. All right, so let me set up another problem. Let's say these are CS departments, and these are CS PhDs. In my other job, when I'm not teaching this class, I'm in charge of faculty hiring. Let's imagine a very simplified model of the faculty hiring process where every CS department has one faculty position that they want to fill. Our department is lucky enough that we're trying to fill 12. Let's simplify. Let's assume that every CS department has one. And so I'm gonna set up some graph where there are a lot more people with PhDs in computer science than there are departments. But I'm gonna put an edge, an undirected edge, between a department and someone with a PhD if this person meets the qualifications that this department wants for this job. So for example, this department might say, we want somebody who does, quantum security for big data applications in the cloud. Whereas this department wants, large-scale distributed machine learning algorithms that are resistant to non-classical physical attacks. That's the same thing. Whereas, this department says, I want somebody that has at least 50 buzzwords in their CV, which is the same thing. But, I want somebody who does architecture, I want somebody who does algorithms, I want somebody who can teach the database class, I want somebody who can teach the intro programming class. You've got edges going between these. Different people have edges to multiple departments, different departments have edges to multiple people. And the goal of the task is to hire as many people as possible. And each department is allowed to hire one person. Each person is allowed to accept one job. Okay? So the output of the process that I'm trying to describe here is something called a matching. Here's one. Okay. So I want to find a maximum matching in a bipartite graph. Okay? So bipartite means that the set of vertices has two parts. There's the part that I've said corresponds to departments, and there's the part that corresponds to people who are looking for jobs. And when I say a maximum matching, I mean a maximum possible number of edges, a subgraph of the given graph, where on either side, every vertex either uses one edge from that subset that I'm finding or uses no edges from the subset that I'm finding. Okay? So the actual hiring problem is somewhat more complicated, and not just by the fact that we have multiple positions and we have hundreds of people applying for each one of them, but also because we don't know the whole graph, and also because people have preferences. They'd rather work at MIT than here, or they'd rather live in Seattle than here, or they'd rather be here than in Kansas. And departments have preferences as well. So the real problem is more complicated, but let's stick to the simplest version. How would we solve it? Yeah, back.
Create a source vertex at the left and a target vertex at the right. The source vertex goes to all these, and the target vertex goes to all the PhDs. Set the capacity of all the rest of the vertices to 1, and just apply the vertex. However, it's called that.
Okay, so the suggestion is I should set up a source vertex that's connected to all the vertices in one part. I should set up a target vertex that's connected to all the vertices in the other part. And the suggestion seems to be that I want to build some sort of flow network. So because this is a source, I'm going to direct all the edges out. Because this is a target, I'm going to direct all the edges in. And now it appears that I'm looking for something relatively familiar. So the suggestion was, let's look for the largest set of vertex disjoint paths in this new graph from S to T. But that's actually overkill because, in fact, I only need to look for edge disjoint paths. Because it's already the case, because there's only one edge coming into this CS department vertex, if I can only use this edge once, then I can only use the vertex at the end of it once. And similarly on the other side, because I have only one outgoing edge from this PhD vertex, if I only use that edge once, then I can only use this vertex once. So in this particular graph, vertex disjoint paths and edge disjoint paths are the same thing. Okay, so you can say, well, I should find a maximum set of edge disjoint paths. Oh, there's one tiny technical detail missing. These edges in the middle, when I got them from the input, they're not directed. So if I want to make a flow network, I have to figure out whether I want to direct these, and if so, in which direction. So yeah, I'm going to direct all the paths, all the edges from left to right. And that will prevent me, when I'm finding these edge disjoint paths, from finding a path that goes from the source to UW, to this guy, to Princeton, to that guy, to Illinois, to that guy, to MIT, to that guy, to Berkeley, to that guy, to the target. And yay, that's a path. Okay, so all of the edges are going to go from left to right. So the only thing that a path can do is start at S, go to one of these, go to one of those, and go to T. Now the edge disjoint path algorithm runs Ford-Fulkerson, and then it runs this flow decomposition thing to figure out what the actual paths are. And so you find these actual paths, and you say, oh, this edge is in one of those paths, so this is one of the edges in my matching. But I can do that somewhat more directly. Once I compute the flow from S to T, every edge, because assuming I give everybody capacity 1, then every edge that is in one of the paths has flow value 1, And those are the edges that I'm going to use in the matching. And every edge that's not in one of these paths is going to have flow value 0, and those are the edges I'm not going to use in the matching. So all I have to do after I've built the source and the target is compute an integral maximum flow, and then take all of the original edges that have flow value 1. Okay? So to get a maximum matching, I add the source, add the target, set the capacity of every edge to 1, compute an integral flow. An integral maximum flow. And then if f from u to v is equal to 1, then I want uv to be in my matching. If and only if. For all u on the left side and all v on the right side. And so overall, this is again going to run in time v times e. Okay? So, great. This is an example, and in fact, this is often referred to as the example of what's called an assignment problem. An assignment problem is a bipartite assignment problem. I've got two classes of discrete objects, and for each object, I want to assign as many things on the left to corresponding things on the right as I can, subject to some resource constraints. Okay, and these constraints sometimes take more interesting forms. It's not just as simple as a matching. So to think of a particular example, conferences in computer science have program committee members. And those program committee members have to review papers. Okay, so here are PC members, and here are papers. And PC members bid on papers. They say, yes, I'm willing to review that paper. So you do get a kind of bipartite graph. Some papers everybody wants to review. Some papers, nobody wants to review, and you have to do something else. But for now, let's just assume every PC member specifies a certain number of papers, a certain collection of papers that they're willing to review. Okay. And then I want to say each PC member can review, I don't know, let's say at most 15 papers. And each paper needs at least 3 reviews. And so I want to know whether it's possible to assign papers to PC members to satisfy these constraints. In particular, that means every paper is going to get I want to know whether it's possible to satisfy. Okay. So this is a more complicated example of an assignment problem. And the way these assignment problems tend to work out when you solve them is I've got these 2 classes of discrete resources, in this case people and papers. Those are going to correspond to 2 different parts of the vertex set, 2 different sets of vertices. There's this willingness, there's this relationship between pairs of these objects that will correspond to the edges of the graph. So in this case, the edges mean willing to review. And then I'm going to have these constraints that sometimes are less than or equal to things that will maybe remind you of capacity constraints, and sometimes are greater than or equal to things that don't quite look like capacity constraints. And you might have an additional constraint here that says each PC member can write either 1 or 2 reviews for a paper, and that counts in the 3 reviews. You know, you can get even more complicated. But those constraints are going to show up in the eventual flow network you build as capacity constraints on certain edges. So to solve this particular problem, I would add a source on the left, and I would add a target on the right. And I would direct the edges in the obvious way from left to right, including the edges in the middle. Now I have to assign certain capacity constraints. The first constraint here that says every member of the committee can review at most 15 papers, this is maybe easiest to see how it would translate. So I need to put 15s somewhere.
Break the PC into 2.
Right. I'm sorry?
Break each PC into 2.
I don't have to do anything quite that complicated. Again, remember, there's only one edge coming into each PC member.
Well, assign 15.
Right, so I'm just going to say all of these edges have capacity 15. Okay, that takes care of this this constraint. The other one is a bit weirder. So every paper needs at least 3 reviews. Now, one way I could do that is I can assign a demand of 3 to every one of these edges on the right, and using this other reduction that I haven't given you the details for, say, well, it's close enough to a flow problem that I just do it. But let me show you how to do this more directly. The idea is I'm going to give every one of these edges on the right a capacity of 3. And what I'm saying is I'm only going to consider assignments where each paper gets, I try to come up with an assignment where each paper gets exactly 3 reviews. Once a paper has been assigned to 3 PC members for a review, I'm not going to assign a 4th because it doesn't help me actually satisfy all the review constraints. Right? And every PC member reviews each paper at most once, so the internal edges have 1. But then the question that I'm going to ask is, if I compute a maximum flow from S to T, this is going to create the maximum possible number of paper assignments that I can subject to these constraints. And when I do that, if every edge going into T is saturated, then every paper has been assigned to 3 reviewers. On the other hand, if I compute a maximum flow and there's some edge over here on the right that's not saturated, that means it is not possible to assign every paper to 3 reviewers. Okay? So after adding these edges, I ask, is the maximum flow value in this graph equal to 3 times the number of papers? If the answer is yes, then the flow itself will give me the assignment. Because I just take each of these edges in the middle, and if it has 1 unit of flow going down it, that means this PC member has to read that paper. If it has a value of 0, then it doesn't. Assuming I've computed an integral max flow. If the answer to this question is no, then I have to go back to the PC and say, really, can we get some people to bid on this lonely paper over here, number 2? Nobody likes it. And PC member number 1, what are you thinking? Come on. You have to review some papers already. Okay, so you go back to the PC and you cajole them into adding more edges to the graph, and then you attempt to do the assignment again. This is actually done in almost every computer science conference I've ever been part of. people actually, no, that I actually do submit a bid for these are the papers I'm willing to review. It's a little bit more complicated because I can say, and these are papers I actually want to review, but I'm not guaranteed I'm going to get them. And then in the background, the conference software actually runs this flow algorithm to assign papers to people to read. So that means that this is a problem of interest to at least one person in this room. Okay. We'll see more of these on Tuesday. All right. Thank you. Exams are up here.